Welcome to this video on Release 19 Satellite, NTN, UAS and Aerial Network Enhancements. In recent years, non-terrestrial networks or NTN have moved from being a specialist satellite topic into the mainstream of 3GPP standardization. The idea is simple but very powerful. Instead of thinking of satellites, drones, aircraft and terrestrial mobile networks as separate systems, 3GPP is gradually bringing them into one wider 5G ecosystem. Release 17 gave us the first major NTN foundation. Release 18 added important enhancements. Release 19 now takes the next step by making NTN more capable, more service ready, and more useful across a wider range of devices and use cases. In this video, we will look at key Release 19 developments, including NR NTN Phase 3, Regenerative Payloads, Store and Forward Satellites, UE to Satellite to UE communication, IoT NTN, Public Warning Support, Air-to-Ground Networks, UAS Phase 3, and Positioning Enhancements. The big message is that Release 19 is not just about extending coverage. It is about making satellite and aerial connectivity more practical, more integrated, and more intelligent. Before we go into Release 19, it is useful to look at the journey so far. Release 17 introduced the initial NR NTN framework. The main focus was transparent payload operation, where the satellite effectively behaves like a relay. The user equipment communicates with the satellite forwards the signal to the gateway, and much of the network processing still happens on the ground. This was already a major step because it brought satellite access into the 3GPP family. It means that phones, IoT devices, and other terminals could start to use standardized cellular mechanisms over satellite links. Release 18 then improved the picture. It added more mobility and service continuity enhancements, better coexistence with terrestrial networks, and further support for regenerative payload concepts. In simple terms, Release 18 helped make NTN more usable and more robust. Release 19 is where things become more interesting. The focus shifts from basic connectivity towards advanced services and new architectures. We now see support for gNodeB functions on board the satellite, store and forward operation, direct UE satellite UE communication, RedCap support, IoT NTN TDD, public warning support, and aerial use cases. So the evolution is clear. Release 17 made NTN possible. Release 18 made NTN better. Release 19 starts making NTN practical for larger scale services and commercial deployments. Let us start with NR NTN Phase 3. This is one of the key Release 19 work items for satellite-based 5G. The focus here is not just to make NTN work, but to make it work better for real devices, real networks, and real services. Satellite systems have very different constraints compared with terrestrial mobile networks. The distance is much greater, propagation delay is higher, satellite beams can cover very large areas, payload power can be limited, and feeder link capacity may also be constrained. One important point to mention here is direct to device or D2D satellite connectivity. This is the phrase many people in the industry now use when talking about normal phones or lightweight terminals connecting directly to satellites. In 3GPP terminology, the wording is more formal. Release 19 talks about improving downlink performance for handset type terminals under NTN constraints. So when you hear direct to device in the market, this is one of the technical areas in 3GPP that helps make the vision more realistic. However, I would be careful with the abbreviation D2D because in mobile standards, D2D can also mean device to device communication. So in this video, I will say direct to device when I mean a device connecting directly to a satellite. Release 19 NR NTN Phase 3 addresses several areas. First, it improves downlink performance, especially for handset type terminals. This matters because a normal smartphone does not have a large satellite antenna or high transmit power. Second, It improves uplink capacity using multiplexing techniques so satellite resources can be shared more effectively between users. Third, it supports multicast and broadcast services when the intended service area is smaller than the satellite cell coverage. This is useful because a satellite beam can cover very large area while the actual service may only be relevant to a smaller region. Fourth, it supports regenerative payload architectures, including a full gNodeB hosted on board the satellite. Finally, it extends support to reduced capability and enhanced RedCaps devices in FR1 NR NTN bands. This is important because NTN is not only about smartphones, it also needs to support simpler, lower complexity devices for IoT, industrial monitoring, and other connected services. So the big picture is that Release 19 NR NTN Phase 3 helps move NTN from a specialist satellite capability towards something much closer to the mobile ecosystem. Phones, RedCap devices, IoT terminals, broadcast services, and new satellite architectures all being considered together. Coverage is one of the most important challenges for NTN. In a terrestrial network, the base station may be a few hundred meters or a few kilometers away. In an NTN scenario, the satellite may be hundreds or even tens of thousands of kilometers away, depending on the orbit. This creates higher path loss, longer delay, and more difficult radio conditions. Release 19 introduces several enhancements to improve the reliability of essential signals. One example is repetition of PDCCH in the common search space. PDCCH carries important control information, so improving the chance that the UE can detect it is very valuable. Another example is repetition of PDSCH carrying message 4. Message 4 is part of the random access process, so improving its reliability helps the UE complete access to the network. Release 19 also introduces repetitions of PDSCH carrying SIB1 within 20 milliseconds. SIB1 is one of the key system information blocks that the UE needs to understand how to access the cell. There is also extended SS PBCH block periodicity up to 160 milliseconds for initial cell selection in FR1 NTN and FR2 NTN bands. The simple explanation is this: when the link is challenging, the network repeats important information, so the UE has a better chance of receiving and decoding it. That improves acquisition, access, and service reliability, especially for handheld and power limited devices. Coverage is only one side of the challenge. Capacity is the other. A satellite beam can cover a very large area. That means many users may be competing for the same resources. At the same time, satellites have limited spectrum and power, so the system has to use available resources efficiently. Release 19 introduces uplink capacity enhancements using inter-slot orthogonal cover codes or OCC for PUSCH transmission. The concept can sound complex, but the idea is straightforward. Instead of treating uplink resources as if only one UE can use them in a simple way, OCC helps multiplex multiple UEs while maintaining separation between their transmissions. In practical terms, this means more users can be supported using the same satellite resources. This is particularly valuable for NTN, where spectrum, satellite power, and beam capacity are all precious. This is also important for future IoT and broadband scenarios. If NTN is going to support not just emergency messages, but also large number of devices, asset trackers, sensors, and broadband terminals, capacity improvements like this become essential. So Release 19 is not only about reaching more places, it is also about serving more users and more devices efficiently. One of the most important architectural changes in Release 19 is support for regenerative payloads and a gNodeB on board the satellite. In earlier transparent payload architectures, the satellite acts largely like a bent pipe relay. It receives the signal, changes frequency, amplifies it, and forwards it. Most of the actual network intelligence remains on the ground. With regenerative payloads, the satellite does more processing on board. It can demodulate, process, switch, route, or regenerate the signal before forwarding it. In Release 19, this concept is taken further with support for full gNodeB hosted on board the satellite. That changes the architecture significantly. The satellite is no longer just a relay in the sky. It starts to become a space-based part of the radio access network. This has several potential benefits. It can reduce dependence on continuous feeder link availability. It can bring some network functions closer to the user. It can enable new service models such as store and forward operation. It can also support more autonomous satellite network behavior, which is particularly relevant for non-geostationary satellite constellations. This is why regenerative payload is one of the big Release 19 themes. It enables many of the more advanced NTN capabilities that we discuss in the next few slides. Store and forward satellite operation is one of the most interesting Release 19 capabilities. In a traditional satellite access model, the satellite normally needs a working connection to the ground segment to complete the communication path. But this is not always available. For example, a non-geostationary satellite may be visible to the UE but may not simultaneously have an active feeder link to the gateway. Release 19 introduces support for store and forward operation for delay tolerant services. The idea is simple. The satellite can receive and store data when the feeder link is not available. Later, when the satellite gets connectivity to the ground segment, it forwards the stored data. A useful analogy is to think of the satellite as a flying mailbox. The UE sends data to the satellite when it is overhead. The satellite carries the data until it can deliver it to the ground network. This is especially relevant for IoT. Many IoT applications are delay tolerant. An environmental sensor, an asset tracker, a shipping container, a remote meter, or an agricultural sensor may not need real-time connectivity. It may be sufficient for the data to arrive later. Store and forward operation therefore allows NTN to provide useful service even when continuous end-to-end connectivity is not available. Another important Release 19 development is UE satellite UE communication. Normally, when one UE communicates with another UE over a satellite network, the traffic goes from the first UE to the satellite, then to a gateway, then through the ground network, and then potentially back via the satellite to the second UE. That can mean more delay, more backhaul usage, and more dependence on ground infrastructure. Release 19 introduces support for direct UE satellite UE communication using regenerative satellite architecture. In this model, the satellite can help route user plane traffic between two UEs without requiring the same traditional ground-based path. It is important to be clear about the scope. In Release 19, this is limited. The focus is on IMS voice and video services between two UEs belonging to the same PLMN and in a non-roaming scenario. Even with those limitations, this is a very important step. It shows how NTN can evolve from simple coverage extension into a more capable communication platform. The practical benefits are easy to understand. Fewer hops can mean lower latency, less dependence on gateways can improve resilience. It may also make better use of satellite and backhaul resources. This is another example of why regenerative payloads matter. Without intelligence on board the satellite, this kind of service becomes much harder to support. So far, we have mainly talked about NR NTN and broadband-oriented capabilities. But Release 19 also brings important enhancements for IoT NTN. The IoT NTN Phase 3 work introduces improvements in three main areas. The first is store and forward satellite operation using a full gNodeB as a regenerative payload. This extends the store and forward idea into the IoT world, where delay-tolerant communication is often acceptable and sometimes expected. The second is uplink capacity improvement. Release 19 introduces OCC support for NPUSCH format 1, which helps multiplex multiple IoT UEs on shared uplink resources. This matters because IoT systems may involve large number of small devices sending small amounts of data. The third is support for broadcasting public warning system messages for NB-IoT. This includes support for warning notifications such as ETWS and CMAS in satellite IoT environments. Release 19 also introduces IoT NTN TDD mode. In earlier releases, NB-IoT NTN was specified for FDD operation. Release 19 adds TDD operation which separates uplink and downlink in time rather than using paired frequencies. This gives more deployment flexibility and opens the door to additional satellite systems and spectrum usage models. The main takeaway is that IoT NTN is becoming more capable. It is no longer just about connecting a remote sensor. It is about scaling satellite IoT, improving efficiency, supporting public warning, and making NTN useful for real-world deployments. Release 19 NTN discussions won't be complete without the mention of aerial systems, including air-to-ground networks and uncrewed aerial systems or UAS. Air-to-ground, often shortened to ATG, is different from satellite connectivity. In ATG, aircraft connects to ground-based cellular infrastructure rather than to satellites. This can be useful for in-flight connectivity and other aviation-related services. In Release 19, the ATG work focuses on improving throughput and making better use of operator spectrum, especially fragmented spectrum. To support this, RF and RRM requirements are specified for ATG UEs supporting downlink carrier aggregation and MIMO. In simple terms, this helps improve aircraft connectivity by using spectrum and antenna capabilities more efficiently. UAS Phase 3 then looks at the drone and aerial mobility side. This includes support for pre-mission flight planning and in-mission flight monitoring, more reliable command and control support, and interaction between mobile network operators and UAS traffic management or service supplier platforms. It also covers areas such as support across multiple USS or UTM regions, network assisted detect and avoid, no transmit zones, and service exposure via the network exposure function. You might wonder, why does this matter? Because drones are becoming connected tools. They are used for inspection, logistics, public safety, disaster response, smart city monitoring, and potentially future urban air mobility. For many of these use cases, the drone needs more than a basic radio link. It needs reliable connectivity, identification, monitoring, control, and integration with service platforms. Release 19 helps bring aircrafts, drones, terrestrial networks, and service platforms into a wider 5G advanced ecosystem. Positioning is another important part of Release 19 satellite and aerial support. For many NTN and UAS scenarios, knowing where the device is located is essential. This can affect service availability, regulatory compliance, mobility, emergency services, charging, beam selection, and application behavior. Release 19 includes on-demand broadcast of GNSS assistance data. GNSS assistance helps a device acquire satellite positioning signals more quickly and more reliably. This can reduce time to first fix and improve the user experience, especially in challenging environments. Release 19 also adds support for additional navigation signals. One enhancement is the introduction of Beidou B2B signal support in AGNSS for LTE and NR. This improves support for the Beidou ecosystem. Another enhancement is AGNSS support for NAVIC L1 SPS in NR and LTE. This is relevant for regional navigation support, especially for India and surrounding regions. There is also the broader Release 19 theme of GNSS independent operation for satellite access. Not every UE may have GNSS capability, and GNSS signals may not always be available or reliable. NTN should not always assume that the UE can depend on GNSS. So Release 19 makes positioning support broader, more flexible, and more globally relevant. This is important not only for smartphones but also for IoT, remote devices, maritime use cases, aviation, and UAS. Let us finish with the key takeaways. Release 19 marks an important step in the evolution of satellite, NTN, UAS, and aerial connectivity. The first takeaway is that NR NTN becomes more robust. Coverage enhancements, repetitions, and improved acquisition mechanisms help devices connect more reliably over difficult satellite links. The second takeaway is that capacity improves. Techniques such as OCC-based uplink multiplexing allows satellite resources to be used more efficiently, which is essential if NTN is going to support more users and more devices. The third takeaway is that the architecture becomes more intelligent. Regenerative payloads and gNodeB onboard support shift some network intelligence into space. This enables new possibilities such as store and forward operation and UE satellite UE communication. The fourth takeaway is that IoT NTN becomes more practical. Store and forward, TDD support, uplink capacity enhancements, and public warning support all make satellite IoT more useful for real deployments. The fifth takeaway is that Release 19 is not only about satellites. Air-to-ground and UAS Phase 3 bring aircraft, drones, and aerial mobility into the wider 5G advanced picture. Finally, positioning enhancements make NTN and aerial systems more globally useful with better GNSS assistance and support for Beidou and NAVIC. So the overall message is this: Release 19 is not just about connecting to satellites. It is about making non-terrestrial networks practical, resilient, and service-rich. It brings satellites, aircrafts, drones, IoT devices, public warning systems, and terrestrial networks closer together as part of a broader 5G advanced ecosystem. Hope you found this detailed video useful. Please like and share the video, subscribe to the 3G 4G channel, and check the links in the description for more tutorials on 5G, 5G Advanced, NTN, and future network technologies. Thanks for watching and see you again soon. Goodbye.